Hi, college algebra. I wanted to take a little time and produce a video for you to watch that kind of does an overview of the graphs for exponential functions and logarithmic functions. We've done some of the exponential, but I wanted to kind of show the various transformations, what they look like on a larger monitor. Maybe a little difficult for you to see on those online videos. And in case we don't have a whole lot of time in class for these, I wanted to provide this supplementary material. So what I want to do is share my screen, and I'm going to call up my Desmos application. So here we go. So you should be able to see my Desmos XY plane. And I think what I'll do is label those axes and maybe make my y-axis extend a little further, kind of make the extent of the axes appropriate. I'll make the y-axis go from -5 to 15, and we may adjust that as we go. Let's cut down the x-axis a bit. That way it'll kind of fit on the screen in a way that makes it helpful, I think. Well, let me get rid of that. And first, I'm going to start with a basic. We've done this a number of times before. You should be able to see this area up here on the left panel, where I'm going to type in the equation of a basic exponential function. Let's make it y equals 2 raised to the x power. And we'll also at the same time identify a few critical points on that graph. So uh, when the value of x, the input is 0, if you replace x up here with 0, y would be equal to 2 to the 0 power, which is 1. And there you see that point on the graph. Now let's put a couple of others here on the graph. Let's say when x is -2, then we would be replacing x with -2. We'd have y equals 2 raised to the -2 power, which is 1/4. And so here it goes, and we'll label that point. And we'll make it blue also like the other one. Okay, and maybe one more. Let's use x equals 3, positive 3. Put that in for x. We'll get 2 to the 3 power, and 2 to the 3 power is 8. Y would be equal to 8, and there's that point. We'll label that one as well. So there is 2 raised to the x power. And now let's just explore a couple of transformations. So on the same graph, I'm going to leave this one here. That's the parent function of 2 to the x. Now let's do a horizontal transformation to the right. So suppose I were to uh, type in the equation y equals 2 raised to the x minus 3 power. So the exponent is x minus 3. So we're replacing x in the exponent with x minus 3. So, for example, the point 0, 1 now, the x value has moved to the right 3 units. So we should see the point 3, 1. There it is. 0, 1 has moved over here to 3, 1. And the same would be true of all the points on the red graph, the original graph, all the points have just shifted to the right 3 units. Okay, and likewise, if I made it x plus 3, all the points would get shifted to the left so that 0, 1, let's make it, yeah, that would be good. Uh, if I replace uh, x with x plus 3, then the point 0, 1 should go over to negative 3, 1. And so now we should see that point. So I encourage you to kind of examine, what's happening here. If you need to pause or stop the video and just look at the graph or watch it again to make sure you can track what's happening there. I encourage you to do that. So those were horizontal transformations by replacing x with x minus something, moving the graph to the right, or x is replaced by x plus something, moving it to the left. So now we'll do a couple of other things. Suppose we were to do a vertical transformation, in which case all we do is keep the original 2 to the x, and then maybe we could subtract. Well, since I have a plus, let's add 4. This should move all the points on the current graph that's red up 4 units. So the point 0, 1, the y value has increased by 4 and is now there. So you see that there's 0, 5 is on the new graph. All the other points would also go up 4 units. Okay, so you can do horizontal, you can do vertical transformations. Now, something we haven't done a whole lot of in class to this point are the compressions and the stretches. A stretch is where I'm going to multiply the original function 2 to the x by a number out in front of it. It could be positive, could be negative. If it's positive, like say 3, the y values would be multiplied by 3. So this point, let's multiply them by 4. So that 0, 1, the y value would move up to 4. We'd be at 0, 4. So the effect of stretching a function is to pull the function away from the axis. So if I put it in front of here, it'll pull it away from the horizontal x-axis. So every point on the original red graph is now 4 times what it was. So 0, 1, the y value instead of 1 is 4. Add 1, 2, which was on the original graph. The y value there is 2. Now it will be 8. Can't see it, but this point, which originally, let me put the label back, at 3, 8, the y value is going to be up at 32. So we'd have to go straight up quite a way. As a matter of fact, I don't know that we can get it all the way up here. So that would be at, what was it, 332. So here's the line 3, and it's right that point. This is x equals 3, and y is equal to 32. So all the y values are 4 times what they were. Now, if I, instead of multiplying by a number greater than 1, let's say I multiply this by, I don't know, maybe 1/3. Then, instead of stretching the graph is compressed, and the y values that were on the original red graph, y equals 2 to the x, are only 1/3 of what they were before. So our original point here at 0, 1, the y value here is 1, but by multiplying by 1/3, the y value is reduced to 1/3. So if I label that point, when x is 0 on that blue graph, y is 1/3. You can see it there. That's this point here. So that's 1/3, which is 1/3 of what it was previously. Okay, we can also do horizontal stretches or compressions. This is where we're going to multiply the value of x by something, not the y value, but the x value. So let's take this 1/3 away. If I go up, and let's say I replace x by 2 times x, that will stretch the graph, in this case, away from the vertical axis. So let's put a 2 there. The graph is going to basically take the points and double the x value. I'm sorry, I said that exactly the opposite. When I multiply by a number bigger than one, it actually compresses it. So the x's are pulled closer to the vertical axis. So the point that was at, say, 3, 8 now is at 1.5, half of 3 and 8. Or maybe a little easier point. Originally, on the red graph, we had the point when x is 1, y is 2. Now the x value is only one half of what it, or excuse me, uh, yes, one half of what it was. So instead of 1, 2, we'd have the point 1/2, 2. So this point here, 1, 2 on the original graph, now is at 1/2, 2. Get that on there. There it is. So multiplying the x by a number bigger than 1 will actually compress the graph and bring it closer to the vertical axis. And then, as you might expect, if I make this a number less than 1, like say 1/3 x, it would stretch the graph 3 times the distance away from the vertical axis. So we originally had the point, uh, let's say, uh, let's get rid of this. The original point on this graph when x is 1, y is 2. Matter of fact, let me put that, label that point. This is the original red graph. There's 1, 2 right there. Now, if I multiply the x and the exponent by 1/3, the value of the x coordinate where the point where this point will move is to 3 times 1 or 3, 2. So we should see that point on that blue graph. And there it is. So this point at 1, 2, that point, by multiplying the x coordinate by 1/3, has moved 3 times the distance away from the vertical axis. Okay, so you can do a lot of things. And then, of course, lastly, to sort of complete everything, you can multiply out in front of everything by, instead of a positive number, multiply by a negative number. So let's say we were to take, let's get our exponent back to simply x. And let's say we just put a negative in front of that. If we do that, essentially that red graph will reflect over the horizontal axis. You're basically multiplying the y values by -1. And for instance, instead of having 1, 2, you'll have 1, -2. Instead of having 3, 8, you'll have 3, -8. So let's go ahead and put the negative in front. And here we go. There it is. So this blue graph is the graph of y equals negative 2 to the x power. The y values have essentially just been multiplied by -1. So let's put that point on there. You'll see that on the blue graph in a second. You still have the same x, but the y, instead of being 2, is -2. And it's right here. This point came down here. 3, 8 would be down at 3, -8 down here, etc. And the last type of, by the way, if you could multiply by a number other than -1, if you multiply by -1/2, or let's make it -1/3, it pulls the graph closer to the horizontal axis. So, suppose this was not -1, but -1/3. Now you can't see it there, but well, maybe you can. Let's take this away. Here's the red graph. By multiplying by a negative number in front, I flipped the red graph reflected over this horizontal axis. But you can see, I think, that the blue graph is not as far away from the horizontal axis as is the red graph. And really, the only other thing we might throw in there is if I replace x with minus x or minus 2x or something, multiplying x by a negative number will reflect it over the vertical y-axis. So these points over here, like 3, 8, will go over to negative 3, 8. So I'm about to put in 2 raised to the negative x power. And there it is. So let me put that point in there. 3 comma negative 8 is now, oh, I'm sorry, it's negative 3, 8. There it is. So by multiplying x by negative x, this point moved over to here, and you can see you've got something that is completely rotated around the x-axis. By the way, that's exactly the same graph. You know, if I have 2 raised to a negative power, that's the same as 1 divided by 2 to the positive x, or 1/2 to the x. So if I replaced, let's put that graph up here. Whoops, 1/2 raised to the x power. That's the same graph we were looking at a minute ago. So 1/2 to the x power is the same as 2 to the negative x power, does the same thing, flips around here. Notice an ordinary graph like y equals 2 to the x skyrockets upward. It's always increasing, and the horizontal x-axis is a horizontal asymptote that the graph gets closer and closer to, no matter whether the value of b, the base, is bigger than 1 or positive 1. Just dictates in which way the asymptote is taking place. If it's bigger than 1, you approach the x-axis going to the left, and you're always increasing as you go in this direction. If b is less than 1, you're decreasing left to right, and the asymptote occurs over here. Okay, so there's some examples of some, well, basically the graph of y equals 2 to the x and various types of transformations that are done on it. Of course, you could have multiple transformations. Just as an example, I could have something like y equals 2 raised to the x minus 2. Whoops, didn't get that right. 2 raised to the x minus 2, which would move it 2 to the right, and then maybe plus 3, which would also, after that, move it upward. So the x minus 2 would move the graph. For example, the point 0, 1 would go to 2, 1, 2 units to the right. And then after that, the graph would go upward. I'm looking at the black graph as the second graph. Goes 2 units to the right and then up 3 units. And you could add additional transformations like reflections or stretching, shrinking, those kinds of compression type of operations. Now, let me suppress this one for a second, the exponential, but we'll hold on to it. Now, the inverse function of an exponential function is a logarithm function. So let me add the function y equals log base 2 of x. And so here it comes. So there's my base 2, x. Now you notice now we've got something that instead of going upward, sort of skyrocketing upwards, in a sense, kind of skyrockets quickly to the right. All right, so let's see if I can scoot this a little bit and then put a few points on here. So remember what a logarithm with a given base is. So notice, by the way, on a logarithm, the domain is only x is bigger than 0, and the vertical y-axis is an asymptote. No longer is the horizontal axis an asymptote like it is with an exponential. So you can see this kind of activity going on. And notice it goes through the point instead of 0, 1 like an exponential. Flip the coordinates around, it goes through 1, 0, which is this point. So as you can imagine, you can do all kinds of transformations with that. Before I do that, let's revisit and put the original 2 to the x graph on there. Okay, and let's also change the logarithm graph, maybe to blue. Okay, so the red is the exponential function y equals 2 to the x. The blue graph is its inverse, y equals logarithm base 2 of x. And, you see a distinctive pattern that I mentioned. One is for the exponential function, let's put a red point on here. Watch the color. So the exponential, remembers the red graph. You have this 0.01. That's 2 to the 0 power. Now let's maybe put, uh, if x is 2, then y is equal 2 to the 2 power. So that would be 4. So this is on the exponential graph, the red one. So there it is. Let's change that one to match the graph color. Okay, so you notice on the logarithm graph, if you flip the coordinates of 0, 1, that's 1, 0. So that is on the logarithm graph. And on the exponential, we have the point 2, 4. So we should see the point if you flip the coordinates 4, 2 on the other graph. And you can see that. Let's make that blue. So every time you have a point on the exponential, if you turn the coordinates around, you'll have a point on the logarithm graph. And in fact, if I graphed the line y equals x, uh, the logarithm graph is actually a reflection of, let me make it dotted, a reflection, the logarithm graph, the blue one, is a reflection of the exponential graph if you flipped it around this line y equals x. So that's something, just kind of a fact to know, and sometimes can give you kind of a sense of, oh, what should this graph look like? Or is it possible the graph I have is the inverse function? So let me get rid of y equals x there. And now just for grins, by the way, comments on the logarithm graph, as I said earlier, now the vertical axis, see, watch the blue graph. This vertical axis is the line x equals 0, and that is a vertical asymptote of the logarithm graph. And so this is when you have a base that's 2, which is bigger than 0, and bigger than 1. If it's bigger than 1, it'll look like this, just for the record. Let's say that, let's put that point back on. Let's get rid of the red points. I'm going to change the red graph to uh, a base that's less than 1, which we can. I can say logarithm base 1/2, for example, or 1/3 or something like that. So let me find my logarithms, which are down here. All right. So here's my base, 1/2, we'll say. Let's get that in there. Hopefully I can type it correctly. Okay, we've got a base of 1/2. Let's put x in here. And if you have a base for a logarithm that's less than 1, instead of coming up like this, it'll still have the vertical axis as an asymptote, but it'll go upward like this. So, one thing that is common between the exponential and the logarithm graphs is no matter whether it's exponential or whether it's logarithm, if the base is bigger than 1, the graph will go upwards. It'll increase from left to right. If the base is less than 1, uh, the logarithm decreases like this. So would the exponential function. So that's one way of kind of just making sure you're on track. Base is bigger than 1. Both graphs, logarithm and exponential, go upward from left to right. If the base is less than 1, both graphs go downward from left to right. Okay, so just to recall, the blue graph is the logarithm base 2. The red graph is the logarithm base 1/2. So let's get rid of logarithm base 1/2 here for a second. And let's go back just to our original logarithm graph, which is logarithm base 2. So let me change my base here. Base is bigger than 1, so it's increasing. Now it's increasing like this, but it's still increasing. And, let me uh, do the usual kinds of transformations. If I typed in x plus 3 instead of x, it'll shift the graph 3 units to the left. So the point 1, 0, the x value 1 would move to -2, 0. So let's keep them both on there, and I'll type y equals logarithm base 2, and I'm going to put x plus 3. And there you can see the point 1, 0 has now shifted to the left 3 units to -2, 0. So this point moved from here over here. And all the same kinds of things would happen with other types of transformations. If I had a vertical transformation, let's say we shifted down 2 units. If I put a -2, excuse me, out here. If I isolated a -2 out here, it would shift the graph 2 units down. So the point 1, 0 would move down to 1 minus 2. The y value goes down by 2. So this point on log base 2 of x would move down 2 units, and everybody else does as well. And of course, you could stretch the graph, you could reflect the graph. Now, without doing a lot of identification of points. So if I wanted to stretch the graph by multiplying out in front, if I multiply by 3, for example, all the y values on the current graph would be 3 times what they currently are. So for example, here's x equals 2, y equals 1. The y value would be 3 times that. So I'd have the point 2, 3. So let's say we had y equals 3 times. I think I can just copy this in here instead of, yeah. So here was the point 2, 1. Now that point is at 2, 3. By the way, just to recall, the definition or the concept of a logarithm, if I took, say, x equals 4 here, let's go back to the original logarithm base 2 of x and replace x with the number 4. So if I had 4, let me just put it in here. Y equals log base 2, not of x, but of 4. It'll just give us the value. I think you can see this here. It says it's 2. And what that means, it's just acting as a calculator now. You're asking the question when you have a logarithm, what is y supposed to be? It's the power you'd have to raise the base to get the answer 4. If I put an 8 there, I'd be asking what power would I have to raise to get the answer 8. So 2, what power do I have to raise it to get 8? It's the power 3. So, just kind of keeping this idea in our heads. What is a logarithm? If I make this number less than 1, then that's going to drag uh, the transformed graph closer to the horizontal axis. I made this like a 1/3. It's going to get squeezed really close to the x-axis. The red graph is the original log base 2 of x, multiplying out by 1/3 now. The y values are only 1/3 of what they were. Okay, if I make it a -1, it's going to reflect that graph over the horizontal axis like that. If I replace x with 2x, it would move the graph, stretch the graph away from the vertical axis. I've done that two times in a row because you have to remember it's opposite. Let me repeat that. If I put a 2 out in front here, it stretches the graph away from the horizontal axis like that. If I put a 2 in front of the x, it makes it closer to the vertical axis. And boy, that is an easy thing to get confused. So multiplying inside, multiplying the x value by something bigger than 1 will take the red graph and put the points closer to the vertical axis. If I multiply by a number that's less than 1, it would move the points away from the vertical axis. So let me put a 1/3 maybe in there. So this point, which is at 1, 0, is now at 3, 0. The x is 3 times what it was. Okay, so those are the compression and stretching types of operations. And of course, I could multiply out in front, say maybe by -2. I think I still have that copied. So this does two things. It reflects the red graph across the axis, the horizontal axis, and stretches the points so that the y values are 2 times the distance from the horizontal axis that they were previously. So I'm hoping that all this kind of business is helpful. I'm not going to, do complicated graphing exercises, but just so you can get a sense for, feel for, recognize, do some simple graphs like these where you know what the original graph looks like of the logarithm or the exponential, know how to find a few points so you can graph it, and then if you need to shift around, stretch, whatever you may do. So just to kind of highlight, uh, let's get rid of the y equals log base 2 of x, and let me put in a table of values. So if you were asked to graph this and create a table of values to begin with, uh, you could create a table of, whoops, for logarithm, and the domain of a logarithm has to be bigger than 0. So let me get that straight to begin with. So maybe we have x equals 1/4. I'm going to create some x values here. And each one is going to be double the previous one. I'll put the y's in there in a second. Um, this will be 1, 2, 4. Now, ordinarily, I might put in maybe 7 points, but to be abbreviated here. Now, these are kind of tricky. If I put in this x value up here, and I say log base 2 of 1/4, ask yourself, what power do I have to raise the base 2 to in order to get the answer 1/4? So the answer is going to be -2. 2 raised to the -2 power is 1/4. And it actually shows that point when, this is kind of spaced nicely because this whole stretch here is from 0 to 1. So I guess this is about 1/4. At 1/2, 2 raised to what power is 1/2? It's -1. These are just going to go up one at a time. 2 raised to what power is 1? 2 to the 0 power is 1. 2 raised to what power is 2? 2 to the 1 power is 2. 2 to what power is 4? 2 to the 2 power is 4. Now, you can sort of see that's sort of the trajectory of the logarithm function graph. And now I'll just put that back in, and we should see the log base 2 of x graph, and it'll go through those points. So that's a good way just to kind of maybe get an example in your head about if I had a simple logarithm graph to create from scratch. Uh, you do have, especially with a logarithm, you have to be kind of strategic in picking the x values. Usually when we graph a function, we'll pick numbers for x like -2, -1, 0, 1, and 2. But effectively, these numbers in the x column are powers of 2. Uh, Another way to do that, by the way, just for example, would be to create a table of exponential values. I'm going to do that here, where maybe I do that, where I pick the usual kind of x values you usually do, -2, -1, 0, 1, and 2. And now this is the value of 2 to the x power, an exponential. 2 to the -2 power is 1/4. 2 to the -1 power, whoops, that's 2 to the -2. Here's 2 to the -1, that's 1/2. 2 to the 0 power, anything to the 0 power is 1. 2 to the 1 power is 2. 2 to the 2 power is 4. Now this is the exponent. And by the way, you can see those points, and that looks like an exponential function. Matter of fact, I might even put that graph up there. That would be y equals 2 to the x power. That's the green graph. And then if I want, 5 similar points for the logarithm graph, since it's the inverse function, I can just take from the exponential table, reverse the x's and y's, and I get this one. So I think I'll stop sharing here, but I wanted to give you something that maybe you can use as kind of a pattern for recognizing and creating some common exponential and logarithm graphs and know kind of what the basic shape looks like. So I'm going to be posting this here shortly, and let me stop sharing. And if you have any questions about that, don't hesitate to reach out to me. But I'm going to end my recording here and then upload it.